Good. So that's what we have done so far: some logistics, full stack, then motivation, and the focus of this course, and the journey for program, and some very high level discussion of ISA. Performance. First of all, when we say performance of computer architecture, what do we really mean, right? In reality, people mean different things, not only latency and throughput. There are also other things. But latency and throughput are the most commonly used, I would say sometimes interchangeably used metrics to measure performance, which is also incorrect a little bit, right? Correct in some cases and incorrect in others. So when I tell you performance in computing system, I either mean latency in general or throughput. And what is the difference, if there is any difference, right? Does it really matter if I measure my performance in terms of latency versus throughput? It really matters a lot, as we will see. Good. So when people measure latency, the word latency means basically time, right? So you are really focusing on a time, whether this time is the execution of a single instruction or the full execution of the program, what we call execution time. At the end of the day, latency is measured in terms of time. This time has a unit of cycle. And when we say cycle, we basically mean the clock period of the CPU. Or in terms of absolute time, like nanoseconds, microseconds, seconds, right? That's basically latency. So it's a time to finish a very non-fixed task. The task can be very small as one instruction, or it can be the full program itself, right? Or multiple programs. And latency is important. Latency is important to simply try to understand for a very particular task. So you have the task to be known. And it's very important to understand how much time this task is going to take, right? So the known part for you is the actual program, task, set of tasks. But the part that is not known is how much time you're going to take in different machines, for example. In that case, you are after time. That's why latency is the important factor. On the other hand, throughput, well, I'm not after obtaining a time a unit, but rather for a fixed amount of time, I'm after how much I can execute. For example, if you have your exam after a week, is this like a fixed time or a variable time? Like if you want to measure your efficiency, performance in that week, how are you going to measure it in terms of latency or throughput? Throughput. Good. That's true. Why that's the case? Because you have a fixed time, it's 1 week, and you might end up finishing your, well, let's say 10 lectures in 1 week or 5 lectures, or maybe finish the lectures and also review some other extra like problems or exercise sets. So in that case, how much work you're going to do in that week is going to be variable based on your performance. But the time itself is fixed, right? So your throughput here is the one factor that will make, well, one version of you different than the other, right? On the other hand, if I'm telling you here is lab 1, right? And then lab 1 might take some groups 3 hours, might take some other groups 10 hours, might take some other groups 3 days to finish, right? In that case, there is a fixed amount of work that needs to be done. It's very well defined in the lab document, but how much time is going to take you is the part that is variable, right? In that case, you measure your finish time, right? The finish time of the lab, which is the task, in terms of latency, right? In that case, the performance here is the latency. I took 2 hours for that lab, right? Or 10 hours for that lab. That's the latency that I consume, the amount of time I consume to finish a very particular task. Good. The difference between them is clear, right? Okay, so if I want to compare, so any performance metric is a relative thing, right? In the 2 examples I gave you, in order to illustrate the idea, I needed to give you 2 different examples or multiple examples of how things really happen. Like for the throughput example, I said you might need to finish like 10 lectures, or you might finish 20 lectures or 5 lectures. So I needed to compare something to something to be able to have a tangible meaning of the performance of the throughput. The same thing for the latency. I said some groups might take a few hours, some might take a few days. So I needed also to do comparison, right? So performance in general is a comparative topic, right? You need to have a tangible feeling of the performance. What do you compare to? Why that's the case? because usually you are after performance to either change a machine or to change an idea and architecture or to maybe purchase a new computer. So you need to take a decision that has a choice element in it, right? Because, for example, architects, when they propose new ideas for chips, they don't say, I have one idea and let's really prototype it. Even if that's the case, your idea involves replacing an existing idea. There's always two ideas that you need to choose from, right? Or you have a couple of ideas, you're not sure which one is going to work. And then you need to basically test both of them, right? There is always a comparison here in terms of performance, especially in competing systems. So when we say A is faster than B, basically, generally, we mean a very direct comparison. We say either the latency of A is less than the latency of B, and throughput of A is larger than the throughput of B, right? We either mean that or that. One very big fallacy in competing systems is people always attribute throughput and latency together. For example, if I asked you, if I have the latency, how do I compute the throughput? What you would say? Well, for a certain task, I have the latency. Like, say, for example, 1 hour, finishing one physical effort, like one in your backyard or something, and then it takes you 1 hour. That's basically a latency, right? So to measure the throughput, can I really get the throughput from the latency? Yeah. Reciprocal, okay. Some other suggestion? 1 over, which is the reciprocal thing, right? So that's basically the big fallacy of throughput and latency relationship, right? In some cases, that's true, but it's not always there, right? Especially again in competing systems. So put this in mind when we are going to revisit it, right? Latency and throughput. In normal cases, they are one over the other. They are the reciprocal metrics of each other. Generally, that's not the case. When I say generally, like in all cases, there are cases where that's not true, right? So don't always apply that thing, right? It really matters into what are the use cases you have, what tasks you have, and what you want to achieve. And we will have examples here where throughput is one over the latency, or the other way around, and there are other examples where it's not the case, right? Just put this in mind because it's very important. So basically, when I make such comparison, well, this is faster than that one. Well, it's quantitative, but not completely quantitative, right? But it's partially quantitative because you know that there is someone that is better than another in terms of performance, like latency is less, for example. But how much less, right? So people don't say, for example, I have this idea and it's better than the existing idea in that chart. It doesn't really work that way. You have to provide a number. Is it like 0.01% faster? Then that's it. It doesn't really matter. We don't need really to bother about it. Even if it's 1.01% faster, why it matters, right? I shouldn't really redesign a new chip, invest into it time and well, energy of employees and trying to do verification only for getting 0.01%, right? Or is it like 10% or 2x faster, right? So you have to provide a more quantitative number into how much faster or slower you are. In that case, when we say there is a machine A that is X times faster than B, generally what we mean is that, first of all, if A is faster than B, that means the latency of B is the larger one, correct? In that case, X will be the latency of B over A, because here that's the part that is larger, or the throughput of A, because that's the part that is larger. A divided by B is also providing X. Make sense? Good. Then another metric that is important, how people measure performance into in computing systems in general or in computers, is what we call MIPS. But MIPS here is not the ISA. It's not the RISC instruction set that we discussed last time, but rather it's simply an acronym of millions of instructions per second. Right? So if we say millions of instructions per second, is this a performance metric or a latency? Sorry, is that a throughput metric or a latency? Throughput. They on the same latency? What do you think? Well, let's think here. Do I have a fixed amount of time? Yes, a second, right? So I'm saying per second. Do I have a variable amount of work? Yes, because it can be 2 million instructions per second, 3 million. I didn't say how many millions do I have. How much do I finish of work, right? So in that case, the work amount is the one that is variable. In that case, it's a throughput metric, right? Well, MIPS in the early days of quantitative computer architecture, again, early 80s, it was very, very commonly used, right? Both in industry and academia. But then people started really criticizing it. Why you think that's the case? Here we are measuring number of instructions, but here I'm equating a simple integer add with a floating point multiply, right? Despite the fact that these are two completely different instructions, most of the time taking variable time, right? So saying I finished 4 million instructions per second, those 4 million instructions can be as simple as a very simple 4-bit addition, or they can be as worse as like memory instructions or floating point operations. So if I give you the two numbers and they are equal, it doesn't mean really the amount of work that has been done are the same, right? Correct? So that's one possibility. Can you think of any other reason? So this is the part that we just said. That's the second. This part that I expected you to get, but this part is the part that's a little bit harder. So let me just explain it directly. And this comes directly from the previous instruction, from the previous section, right? Last lecture, we discussed, for example, CISC versus RISC, right? And we said one big difference in the spirit of the two classes of ISAs is that in CISC, you back multiple operations in one instruction, right? So in an add operation, for example, let me see if this thing runs. And no. Okay, good. So let me use my pen then. So if I look into, because it's important to have a feeling of this thing. If I look into a simple CISC combination instructions, simple CISC add instruction, I can have something like add, and then here R1, R2, R3. Usually when I have these brackets, what do they really mean in assembly? Those square brackets, what do they really mean? Address, exactly. It's a memory address, right? So in a CISC operation, the add can really operate, as we said last time, directly in the memory addresses. If you think of the amount or the number of operations that I need to do to execute this single instruction, what do I need to do? What do you think? Can you enumerate the operations that you need to finish in that instruction? Load, exactly. Is it one load? Two loads, basically to obtain your two operands, right? Bring them from the memory. And then, so now I have two load instructions. Okay, and then do what? After I obtain my two value. Yeah. I add them, exactly, thank you so much. So I obtain the two operations and then I add them. It's like 3 sub instructions, yes. Oh yeah, this is an add instruction, but this is CISC operation. I guess this was the question I couldn't answer. Okay, so basically this is an add instruction. But add in CISC, as we said last time, it really backs multiple operations. So they can operate directly into memory instruction. In that case, the add, to be able to execute it, first of all, you need the operands, the values need to add, right? But those values are in the memory. So you need to go first to the memory and get them, right? So why it's an add instruction, but internally it has two load operations, right? To obtain these two values, R2 and R3, assuming that these are the source operands and this is the destination. So this is a complex instruction. That's why it's called complex, because it entails multiple operations, right? So it said there are two loads, one add, and then what? After I add the operation, what do I need to do? Store. Then I need to write back the results into the memory. So I had really 4 instructions into a simple one instruction. Good. If I'm doing this in RISC, as I guess your friend question here was, then what I need to do is one instruction is doing one thing. Then I need first to load maybe in, let's say in R4, the value from R3. Then I load in R5, the value from R2. And then I do the simple add R4, R5, and put this maybe in R6. And then I do a store operation of R6 into R1. right? Makes sense? So now, why this discussion is relevant here? Yes, you might see that, right? If I'm telling you I'm executing 1 million instructions in an Intel machine versus I'm executing 1 million instructions in an ARM machine, what does it even mean? It means nothing, right? I cannot really compare these two numbers. It's not an apple-to-apple comparison, right? 1 million instruction here might mean so many things. Here, what might mean a completely different small subset of it, right? So I think people think that MIPS is in fact not a very representative metric because I cannot compare two programs to each other because in reality, what the programs are doing in terms of actual instruction, whether it's add, multiply, etc., will differ. And at the same time, I cannot compare two machines with two different ISAs together. And in that case, when can I use MIPS? This is basically one school of discussion that is completely useless, right? But you see the reasons, right? And yet they are convinced, right? Then why people have been using it? Is it really completely useless, or there are cases where MIPS can be the good thing to use? Yeah, the same workload, please, right? So if you have the same workload and you have the same ISA of the same machine, but for example, you are proposing to improve your pipeline, you're not adding a new instruction, but you are making one block faster, right? Or you are simply adding a prefetcher, as we'll see, or adding another cache. In that case, you are making a small change inside the same processor with the same ISA, and you're going to run to compare the same application across the two different IDs. In that case, MIPS will be, in that particular case, MIPS will be useful, in fact, right? Because it's the same program, same processor. So that means the translation will be exactly the same. We no longer have that problem. And the concern about executing multiply versus add. It's useful in certain cases. Make sense, or there are questions? Good. Okay. So generally, if I want to measure, and this equation is very intuitive, as we will see right now, and that's the general equation that everyone almost is using in terms of measuring performance. So if you want to measure a performance of a CPU and a certain program, what elements do I have? For the program, I have the number of instructions of the program, right? And then for the processor, I have how many cycles I take per instruction. And then simply, also I have the frequency of that processor, right? Because here, when I say cycle, in one processor, one cycle might be 1 nanosecond. Another processor, this cycle might be 10 nanoseconds. So you run it, right? Good. So generally, if I want to measure the total execution time of a program, I would say I have the total number of instructions, multiply this by number of cycles for each instruction, and then you simply transform this into actual time by doing seconds per cycle. So first of all, is this throughput or latency?
Yes.
Latency, definitely, right? Because you can tell here I'm transforming everything into absolute seconds, right? That's one important thing. And then instructions per program. Is this like a program artifact? I might have already answered that. Is this a program artifact or a CPU artifact? Something related to the architecture or related to the application? First element here. The application, right? So no matter what processor you are targeting, if you have one application, I mean, as far as the same ISA, you will end up having the same number of instructions, right? So it's an artifact of the program and in part the compiler, because the compiler might optimize the number of instructions. And then the second one and third one, as we said, is an artifact of the actual architecture, right? Sometimes you propose things, or you have a processor that runs in a higher speed, and basically also how much actual latency you take in a single instruction. This is the second element, number of cycles per instruction. Good? Are we good? Like, do I understand the three metrics? And simply how we have the total execution time. Now, instead of every time we write an instruction per program, cycle per instruction, second per cycle, usually people for the cycle per instruction, they have, and this notion is very, very common in computer architecture, they call it CPI, right? CPI is basically cycles per instruction. There's another metric that is related to this. It's called IDC, which is instructions per cycle, right? As you can tell, CPI is a latency or throughput metric. What do you think it is? Latency is cycles per instruction. So we have one instruction and we have variable amount of cycles. So this is latency. What about IBC? Instructions per cycle. Now I'm fixing it one cycle, and how many instructions I finish is variable. So IBC the throughput, right? So generally, CBI is a latency metric, and IBC is well, CBI is a latency metric, and IBC the throughput metric. Makes sense? Is anyone confused? If you're always confused, you don't have to worry. Think about, well, am I really after measuring latency? Is the actual output at the end is in terms of cycles or seconds or some absolute notion of time? Or I'm measuring amount of work that's being done in a fixed amount of time, right? That's really what matters. And then seconds per cycle is the actual running frequency of your CPU. Now, another very important point of discussion here is this second and third metric. When you say, well, I increase the running frequency, at one point, maybe not much nowadays because the frequencies of actual laptops are almost stabilized. But 10 years ago might be. Most of the performance you were gaining out of any new machine, for example, any new generation from Intel, was due to only one thing, which is basically increasing the clock speed, right? So at one point, we were running at 1 gigahertz. Then Intel used to have one new machine or one new architecture every 2 years, and almost it was doubling in frequency, right? So we reached 1, 1.2, 1.5, 2 gigs, 2.5, 3 gigs. All of a sudden just stabilized, right? So for a period of 10 years, around 10 years, all of the gains that computer architects were really getting was purely from increasing the transistor count and doubling the clock speed. There was almost no, I would say, drastic innovations into the actual architecture levels. Good. So at that time, when I was teaching these classes, I would say, well, a very common method, I would say, if you're going to buy a new laptop, you look for the high speed, right? If it is running a higher speed, then that's it, right? But now in this slide, you learn that's not true, right? Because the phone metric is what really matters, right? When you buy a new laptop, well, which metric of these three don't really care about, or maybe irrelevant here? If you buy a new machine, yeah. Instructions per program, because in fact, well, that's irrelevant. You're talking about I'm purchasing a new hardware, and well, the programs are going to run, they'll be the same. They're called consumer programs, so it doesn't really matter, right? So you're not changing. So usually people drop this term from the equation, right? Now the problem was you are left with two terms of your performance, but you are only focusing on one of them. So higher speed means overall better performance. That's not true, because in most cases, especially nowadays, when increasing performance is increasing frequency is very, very problematic, then if you try to increase the frequency of a machine, most of the time it's coming really at the expense of increasing also the latency, the cycles per instruction. You have to look into the overall collective metric, right? So don't get fooled by the marketing namings that simply, well, this is double clock speed, you're getting double performance. This, in fact, does not implicitly mean that, right? This is not a correct conclusion out of the introduction that was given to you, right? Good. So cycles per instruction, this is our second element here. We call it CPI. And there is one other element of discussion for the CPI. Yeah. Yeah, this is a total execution time, which we said this is a latency metric, correct? If this is a latency metric, we said to have a better performance, do you want to increase or decrease? You want to decrease, right? You want to decrease the overall time. So in that case, every single metric of this, you want to decrease, correct? Yeah. So what? To decrease the last one, seconds per cycle, what you can do? Video frequency, right? Because it's basically, this is your clock value, right? To decrease your clock value, you need to increase the running frequency, right? So this is the part that we said, well, most of the time we got the gains from. So the increasing frequency entails directly reducing the part, right? And then the second part, CPI, cycles per instruction. If I want to decrease that one, I need to optimize my latency, right? I need, for example, if I know that my multiply is taking 20 cycles, I can add a new multiplication unit that's really optimized and takes only 5 cycles. In that case, I optimize. And we're going to discuss this in more detail because there are multiple open questions here that we need to discuss. Well, the first one is the one that is less related to computer architecture and more into compilers and also writing efficient programs. 4 instructions per program. If I want to decrease the number of instructions per program, maybe for the same exact piece of software, the compiler, as we said earlier, might generate completely different. It's a one-to-many generation, right? So it depends on how better your compiler is optimized. You're going to generate less assembly code, less number of instructions. You basically give to the hardware less work to do, right? And if this is less, the overall execution will be less, correct? But again, here, one of the open discussions is that the number matters less. In fact, the type of the instruction matters more, right? Because if I have 20 add instructions versus 5 division instructions, in fact, the 20 adds are big, right? Because usually a division takes 20x the latency of an add instruction, right? If I can really increase my arithmetic operation, arithmetic number of instructions, but decrease my memory operations, then in that case, I would also have a better execution time overall, right? So this number, we have to take with a grain of salt. Numbers matter, but also the time of the instructions really matter. Right? And again, part of what we're going to do in lab 1, we're going to look into programs, and then look into the generated profile of the program from Maxim, and identify the types of the instructions that are being executed. Do what we can call a histogram of a program, like simply say this program is composed of 20% arithmetic operations, 50% memory operations, 30% branch operations, right? And then based on this analysis, you make suggestions of what is the bar that you really, if you optimize the most, will give you the maximum gain. And then you go ahead and reduce the latency of the bar in the simulator, rerun the program, and look into the new execution time. And you see if you obtain the gains you were looking for, right? So this is basically what people will be doing. Look into a program, look into the type of the operations that are very common, and optimize. Generally, later on, we will see that there is a very common statement in computer architecture, which is called optimize the common value, right? If you have something that appears again and again and again in the program, then you optimize it to get the maximum gain, right? We're referring to it as Amdahl's law, and hopefully the remaining 10 minutes at least we can revisit. If not, then tomorrow we'll continue. Good. So now let's have an example of how we can really understand CBI or have a tangible feeling what it really means. Assume I have one program, I call it program A, and then I have 3 types of operations for that program. The 3 most common ones in addition to branches. There's integer operations, floating point operations, and memory operations. Right? Then I'm telling you that for the integer operations, you're taking 1 cycle. For the memory, you might be taking 2 cycles. Very simplistic, non-realistic numbers, but just to have a feeling of it. And floating point might be taking 3 cycles. Now, what is the CBI, right? So if I go back to this equation, just to tell you why we're doing that stuff. When I say cycles per instruction, you might have imagined that if I'm giving you an application with 1 million instructions, then I should also tell you that every instruction takes 2 cycles. In that case, you multiply this one by this one, right? The problem is, as we were saying, not all instructions are taking the same cycle per instruction. So in that case, I can take the full number of instructions of a program, which is this one, multiply it by the cycle per instruction, because this one differs from one instruction to another. What can I do? Well, I can take 2 directions, and both at the end mathematically are the same. I can say, instead of taking the full, you know what, maybe I should really write this down into, now I don't remember where did I put the pen. Okay. Let's exit that. And I okay, so I can take 2 different directions. One of them is to say, and first of all, let's write our big equation up here. Number of instructions per program multiplied by cycles per instruction, and then this is basically multiplied by the clock speed, but forget about the clock speed for now. This one, the problem is that it differs from one instruction to another. So I can say, instead of taking the full number of instructions per program, well, take the number of well, I wouldn't say add, but rather integer arithmetic instructions per program, multiply it by the CBI of the arithmetic instructions, right? And then add into it the number of floating point instructions per program, multiplied by the CBI of the floating point. Plus, take the number of memory operations per program, multiplied by the CBI of the memory operation, right? So now I have divided my equation into three main parts, right? Why? Because I realized that this number is not one for all, but instead I need to decompose this one into the one that matches the CBI they have, right? Makes sense? This equation is exactly still the same as this one. It's refined to reflect the fact that CBI differs from one type to another. Does this make sense? If there are questions, please ask. So simply, if you think about it, I gave you amount of work to do, composed of, again, 1,000 instructions. And then I'm telling you, well, not all instructions are the same. There are types that will take you 1 hour to finish, others that might take you 3 hours to finish, and others that might take you 10 hours to finish. In that case, to get the total execution time, you will tell me, okay, out of these 1,000, I'm going to decompose them into the 3 types, calculate the execution time of each type, and then sum them up, right? That's really how it works, right? So it's very intuitive in that sense. Then the other might be faster way of doing it is to say, at the end of the day, if I want to obtain the average execution of a single instruction, I have to divide by the end of the day by the total number of instructions per program, right? So if I'm after calculating the effective CBI, right? Why I'm after effective CBI? Because one application here is a little bit irrelevant, right? If I give you one benchmark, then what about the other one? So we want a metric that is independent of the program. CBI is the one that is independent of the program, as we said earlier, right? It's basically an artifact of the CPU architecture itself, correct? So in that case, I'm normalizing to the total number of instructions per the program. But mathematically, this is an average, right? This is saying, well, you're summing up the different works, dividing by the total number, that's an average number, right? So the other way of doing it is to say, well, instead of doing this, I'm really going to very, I would say, not even high school, but maybe 6th grade, 7th grade math, is simply to distribute the denominator over everyone, and they say, okay, the number of arithmetic divided by the total number, and then multiply by the CBI of the arithmetic, plus the same thing for the floating point. Plus the same thing for the memory. Correct? But what does this metric really represent here? It represents the ratio, the percentage of integer or arithmetic operations in my program, right? So if I'm telling you, you instead have 20%, so if I go back to our original example here, I'm telling executes equal. What does it mean really by equal? It's something like if there are 3, it's 33%, 33%, 33%. But that's not usually the case, right? Usually in a given program or in a given problem in computer architecture, people tells you your program is composed of, let's say, 50% integer operations, 20% floating point operations, maybe 10% branches or control flow instructions. What are we left with? 20% maybe memory operations, right? So I'm giving you the percentages, and then you're going to use those to calculate the actual CPI. How do you do this? Well, if I'm telling you one integer operation is taking 1 cycle, this one is taking 10 cycles, this one might be taking 5 cycles, and this one might be taking 50 cycles. then the actual CPI will be, it's 50% multiplied by 1 plus 20% multiplied by 10 plus 10% multiplied by 5 and then 20% multiplied by 50, right? This is basically the CPI average of the overall program. Make any sense? So I need to do the full math with you just to make sure the first time you get the idea, right? Make sense? Yeah. Out of the integer, you mean? Like from this. Yeah, well, those 4 are also not fixed, right? For example, I ignored other 5, like example, logic shifting operations. I'm just giving you as an example that the most common ones. Arithmetic usually is either integer or floating point, right? So usually people tell you, and well, you have an integer arithmetic operation, floating point arithmetic operation, and people differentiate them because floating point takes way more time, specialized hardware than an integer one. No, this is basically a different problem than this one, right? This one is dividing all the applications, dividing the benchmark into equal classes, like 33% each. This is what it means by equal, and then it giving you different numbers, right? So this is a problem, and this is another problem. Above here, you mean? Yeah, correct. That's, well, before you divide, this gives you a running time. After you divide, that's the average. That's correct. Yeah, the total number of instructions build the program. That's basically the average. Let's stop here and we'll continue tomorrow, okay?